Speaker is Mr. Brian Beckman. Brian is a cyber researcher at the Idaho National Laboratory. He has a bachelor's in electrical engineering from Brigham Young University and a master's from the University of Nevada in Las Vegas in electrical and computer engineering. Brian's a busy father of 6 and currently works at the lab within the National Homeland Security's Critical Infrastructure Protection Group. And I turn it over to Brian.
All right, thanks, Shar. Wanted to thank you for that introduction. This is Brian Beckman. My colleague is Jed Hale. We work at Idaho National Laboratory. We're in the National Homeland Security and Critical Infrastructure Division. Today we're going to talk about a tool that we developed called WeBin. That's the title of the original paper was Binary Analysis with Architecture and Code Section Detection using Supervised Machine Learning. So a little quick introduction, and we'll address the problem that we're trying to address here. So knowing what's inside of a binary file is becoming increasingly more important. Malicious actors are introducing malicious code at low levels, firmware levels, increasingly more recently. This is an issue in both IT environments as well as OT networks as well. Especially true in SCADA type systems, water, power, gas, where updates are often infrequent due to the downtimes required. Also, the potential side effects of these malicious binaries can be very severe. It can have real world impacts, lack of power, water, gas. So the first step to being able to know what's inside of a binary file is being able to disassemble and reverse engineer that file to understand what's going on inside. To be able to reverse engineer properly, you first need to be able to identify the architecture and where the data in that file exists. WeBin, that's our tool, accomplishes these tasks using supervised machine learning. Again, this problem is important in all networks, OT networks in particular. So a little overview about WeBin. WeBin is an acronym, stands for What Is It Binary. It is, like I said, a tool developed here at Idaho National Laboratory with the purpose of aiding future reverse engineering and disassembly tasks. This is a continuation and enhancement of work previously published by John Clemens at the University of Maryland, Baltimore County. We use supervised machine learning models. We use a number of different models. With those, we are able to calculate endianness, predict architecture, and locate the data offset within a binary file. And if anybody is familiar with supervised machine learning, this flow graph here on the bottom should be very familiar. We'll start with the training data, has labels attached. We go through a feature extraction step, which I'll talk about shortly. You then set up and train your model. The unlabeled data gets fed in. The same feature extraction occurs. Within your model, you're able to predict, and your results are labels. In our case, the labels are going to be architectures. So this slide here shows, we're going to talk about byte histogram. This is the feature extraction portion that I referred to earlier. So a byte histogram is a process of taking the raw hex values of a binary file and essentially binning them, counting them up, putting them in their in an appropriate bin. I have an example here. So we have our binary example of the binary hex file here. We then take those values from 00 to FF, so hex 0 to 255, and we count up the number of occurrences that happen in each. Those values are then normalized to range from 0 to 1. On the right-hand side here, we have looks a lot like a spectrum. The bottom axis is value is 0 through FF, and we have the normalized count on one side and the full count on the other. And just looking at this with the naked eye, it'd be very hard to determine which of these peaks are important, which ones represent a particular architecture. But we found that with the supervised machine learning, these features, this vector that's generated, is very well suited for detection and architecture prediction. Again, this byte histogram process is the critical piece for Weebin's ability to detect architectures. So first piece that Weebin does is it calculates the Endianness. If you're not familiar with what Endianness is, there's a big endian and little endian, and it refers to the order in which the bytes occur within a multi-byte value. So for a big endian file architecture, you would have the most significant byte would occur first, and the least significant byte would occur last. With little endian, the reverse is true. It is also, we use the fact that it's very common for binary code to increment a variable or add one to a stack pointer or anything like that. So it's very common to add one to a value. That the fact that one will occur frequently within binary code, and the fact that there are different representations based on big endian or little endian, we were able to, in this bottom left-hand side, show a piece of pseudocode. This is how endianness is calculated. So we look at the number of instances of the 0001 representation versus the number of 0100 representation. If one occurs more frequently than the other, we attribute a flag, a big endian flag of 1, a little endian flag of 0, or vice versa. Those flags are appended to the vector we had previously included. And so the Endianness is important because there are architectures that exist where Endianness is the main discriminator between the two different architectures. And being able to determine this, being able to calculate this allows Weebin to better discriminate between those architectures of that type. Okay, the meat of Weebin is the ability to detect the architecture. So we first had to come up with a training data. We extracted that from Debian distributions, which came pre-compiled for different architectures. We selected a number of architectures that we were interested in, and we used those binary files that were extracted. We sent them through the byte histogram process that we referred to earlier. We then fed those into 8 separate machine learning models. We have those listed on the lower right here. Those were used to train our 8 models. The byte histograms for our test data, our unknown data, had a similar process. There are also times where you may not have a complete binary file. You may not have 100% of the original file. Times like that might be data corruption, if you intercept a file over your being transmitted over your network. If you're doing some triage, trying to undelete some files, they might not come back complete. To determine how much of the file we needed to accurately predict architecture, we extracted contiguous portions of the original file. There's 90%, 80%, all the way down to 10% of the original file. And you can see at 100% of the original file, we have very good results. A low of 91%, a high of 100%, an average of just shy of 98% accuracy. As you reduce the amount of the file that exists, the accuracy goes down a little. There was what we found that with the SVM model, we could achieve results as good as 80% with as little as 20% of the original binary file. And this is important, like I said, because there will be times where you don't have the complete file, and you'll still need to be able to determine the architecture to determine if this particular file is a candidate for reverse engineering. Continuing with architecture, So we got good results to begin with, and we wanted to see if we can improve those results. There are a number of noise bytes that occur, or we are referring to as noise bytes that occur within binary file. Those are typically values where data is encrypted or compressed, or just repeating values that are used to align different sections. We utilize binwalk, which is an open source binary analysis tool that is able to calculate entropy. Entropy being just the randomness of the data within a file. On the left-hand side here, this black yellow graph, we have an entropy chart from binwalk. This is of a firmware file. The upper section we have highlighted in red is a section of very high entropy. This is very random data. Would typically be data that is encrypted or compressed. Encrypted data would not be useful for Weebin. Compressed data, unless you were able to uncompress it, would not be useful either. On the bottom here, we have the low entropy section. These are typically repeating values of 0, 0 or FF, used to align different sections of a binary file so that they occur at particular offsets that are desired. So we, similar to the previous slide, we have a chart here. We started with 100% of the file and did some reductions in percent of file against all of our machine learning algorithms. And you look, you can see previously we had 80% accuracy. We've now got 82% accuracy, so a little bit of improvement. We weren't expecting a huge improvement, seeing as how our results were very good to begin with. The bottom chart here shows the delta between the chart above and the chart on the previous slide. So you can see that the green sections are percentages of improvement. The red are sections where there were a little bit of a reduction, and the yellow is sections where there were no change. So overall, you can see that there was an improvement in the percentage of accuracy for architecture prediction. The final step that Weebin does to help with reverse engineering is it helps locate where the data offset exists. Data offset being where those opcodes, where those instructions reside within the binary file. To do that, we took a binary file, typically a larger file like a firmware, for instance. We split that file up into subfiles that overlap. We then took each of those files and processed it through our machine learning models. We did all 8 machine learning models independently, and the predictions are compared. Where the predictions agree are the sections where the data and the instructions, those opcodes, are concentrated. So I have an example here. On the left, here's again that entropy graph from binwalk. You have a section highlighted here that corresponds to the section below in this graph where there is agreement between the 8 algorithms as to what the architecture is. The 8 architectures here are listed on the left, and the algorithms are listed on the bottom with separate colors. On the right-hand side, we have another firmware file with a much smaller area of agreement. Again, that's highlighted below. And in this case, the agreement was that this is a PowerPC architecture, whereas the previous there was agreement that it was an ARM64. And again, knowing where the data exists is key to know where to start your disassembly, where to know where the data is and how to take that apart and know what's inside. So in conclusion, Weebin allows for the calculation of endianness, prediction of architecture, and the location of the data offset. You can get really good results with this very small portion of the original binary file. In our case, 80% with as little as 20% of the original file. The fact that it uses supervised machine learning allows us to allow for additional architectures to be included. There might be new architectures, exotic architectures that are important to a particular industry that can be trained. With proper training data, you can include those as well. Future possibilities, again, adding additional architectures, a user interface, a GUI for ease of use. The big one would be the speed. the Weebin was developed as a proof of concept, and speed was not a factor that we considered. So with multi-threading, multi-processing, that could be sped up quite a bit. And again, Weebin, this is a tool to help aid in reverse engineering to know what's inside your file before or after it gets introduced to your network. If a malicious file gets introduced to your network, the results can be have real-world consequences, and being able to know what's inside of a file will help you determine whether that file should be introduced, or if it is introduced, how to best remediate it to recover and get that back, get your system back up. Again, my name is Brian Beckman. My colleague is Jed Hale from Idaho National Laboratory, and we just talked about Weebin. Are there any questions?
Thank you, Brian. It appears that we have no questions in the question box yet. Maybe some people will ask some, but while we're doing that, I think I prepared a few. I was curious, can you explain, you do a really nice job with talking about detecting these binaries. Can you explain the aspects of your work that align with resiliency?
So in my mind, being able to recover from the introduction of a malicious binary would be a feature of resilience. Being able to bounce back from something getting introduced, or better yet, preventing it from being added to your network in the first place, would help have that resilient nature for a network.
Okay. We do have a question from the question box. So, aside from architecture detection, do you think you could receive other information from byte histograms?
Probably could. You could probably, depending on the type of file, you could probably might be able to determine compiler types, what optimization flags were applied, things like that.
How does Weebin work on packed files or obfuscated files?
So packed files, if you are unable to unpack those files into to raw binaries, it would have difficulty determining the architecture. That's, like I mentioned earlier, the compressed files. If you're unable to uncompress them, they would be treated as encrypted files, which would not be of use to Weebin.
Okay. How about obfuscated files? Same problem?
Files would be similar.
Okay. Any other questions in the room here, in the chat room? Doesn't look like it. So I believe we are done with you right now, Brian. And so thank you very much for that talk.